All right, good to be here. I love this conference. I'm going to talk about things that I often talk about. It involves some recent work with my former postdoc, Les Riedel, and some very old work with a friend of mine who's retired from IBM back to like the 1980s. And here we're going to talk about just a very small, little, not very important things that don't have to do with much. Like the relation between dynamics and computation, self-organization, whether to believe anything you hear, and what it feels like to be inside an unobserved superposition. That's all. Yeah, that's all. Yeah. Then there'll be a question period and a panel discussion. Okay, so the question that the cosmologists face, how does this complicated world that we live in emerge from the very obscure laws of general relativity and quantum mechanics? And maybe I've heard people here say, there's got to be something more, which my instinct is that just makes it even worse. And I've spent most of my life thinking in a more terrestrial scene from how do we get it from basic laws of physics and chemistry that we thought we understood at some level. But the notion of complexity and the fact that the word has been used to mean so many different things is part of the problem. So here's my approach to that, and that is that I say, well, let's try to find really simple, classical, discrete, even systems that exhibit this intuitive feeling of it starts with simple and becomes complicated. Complicated in a more non-trivial sense than just being random. So this is a cellular compound that I've been working with for a long time in one dimension. So time is going left to right, which is, I guess, one of the least used conventions. And we have a periodic initial condition, and there's a small defect here, and it produces this kind of deterministic wave. Now, this is not like your usual one-dimensional cellular automata. This is a reversible one, so that if you look backwards in time, we're more or less doing the same thing. So it was simple at time zero, becomes complicated in time future, and complicated in the past. And I'll just tell you what the rule is. You guys might enjoy playing with this yourself. I don't think anybody else has much played with this compound. The rule is it's an Ising model, but deterministic, so it's energy conserving. And the rule involves two time steps. There's the past and the present, and then from that you calculate the future. And the future is equal to the present if is different from the present if exactly two of the four nearest neighbors, not counting the site itself, is on and two are off, or up or down, whatever you want to call it. And in other cases where it's unequal, it stays the same. So you can think of this as conserving the energy of sort of an interaction between this site and this site and this site and this site and so on. And if flipping it doesn't change the energy, then you don't, not only can you flip it, you must flip it. So this is the rule. And you can see it generates some periodic behavior of very, very trivial sort, and then this pseudo-random behavior like that. So this is a simple cause with a complicated effect. And before I go on to say that in a way, this effect, by fact that is complicated and yet deterministic, means that if you took a piece of it like this, a big enough piece, you would have good grounds for inferring this whole evolution of which it's part. So this is analogous to the fact that if you take DNA out of one person, you've got a pretty good idea of the DNA and anybody else in the room, and also a lot of ideas about the history of the Earth.
Did I understand correctly that you look not just at the past time step, but the one before that also?
That's right. The present is a function of the two previous time steps.
I see. Okay.
It's a second order discrete processes in the way this in Newton's laws of motion are second order.
Okay.
Yeah. So that's a nice feature, which is our complexity is full of it. That is that we can find if you went to the moon and you found a bottle cap, you would know tremendously, exponentially more than the information in the bottle cap about the moon's history could be. So now, how do we want to formalize this notion? Well, Occam's razor, the idea that we should always use the most economical hypothesis, has been around. I believe it was invented by Aristotle, and it's mostly honored in the breach rather than the observance, because scientists will say, well, when they see some new theory, like I say, well, somebody says, oh, we need something more besides quantum mechanics and gravity. I say, well, that is hopelessly complicated. It should be rejected on the grounds of Occam's razor. It's too strange for me to think it's simple, so it's mostly an impediment to science. But anyway, what we're supposed to do is to choose the simplest explanation. And we do that without regard to the length of the deductive path connecting it to the phenomenon it explains. So the way to go here is to computerize this. So we take our phenomena that we want to explain, and we digitize it, and we're digitizing everything these days, so we might as well digitize nature. And then we also, well, let me set the word, go into the, I'll go one step forward, but, okay, so we'll replace the hypotheses by inputs to the computer. Well, what kind of computer? It's a universal computer, and we want to make it simple. We want to give it a random input, or the possibility of receiving any input. So we put a monkey at the keyboard, and the monkey is not typing on a typewriter because it's hard to find a typewriter anymore, but as a universal computer. And this algorithmic information theory is the theory of what you would get if you have randomly programmed a computer that is universal, so it is capable of doing anything. And this, the tree of possible computations of this computer is a kind of an object of almost cosmic holiness that you can contemplate. It's a sort of microcosm of everything that you can know by deductive reasoning or numerical simulation. So typically, if you put in an input like 0, and then you put in another 0, and then you put in a 1, the computer behaves like a typical computer and says syntax error. Or if you put in a 1 and a 1 and a 0 and another 1, then it just goes into a non-terminating computation where it just eats more and more inputs and never does anything with it. So it does all sorts of bad things. It also calculates the infrared spectrum of toluene and the best, which side to play if you want to play chess and win for sure. And then since computers can simulate themselves, this graph this tree is self-similar. There are infinitely many nodes in which the computer just does the same thing as the computer from the top. So that's a kind of thing to dream about when you go to sleep. And now we go back to our Occam's razor. We've digitized the phenomenon, and the alternative programs, these are alternative things the monkey might type in, and we look at them all and we say, well, there are all different ways of producing this thing. For example, you could put in something which just told the computer to print whatever I'm next going to give you, and then type in the verbatim description. Call that a print program. But we'll choose among these the smallest one, the shortest in number of bits. And that's what's used in algorithmic information theory to formalize the information content, or randomness content of this string here. But here we use it as the criterion to select which evolution we believe. So since this is shortest, we say, given this that we see, it probably came by this path. And the length of that path is the amount of complexity in the sense that I'm talking about, which I call logical depth of this string. This duration is the logical depth of that.
Why do you say that it's the most likely? It seems to me that
Because-
it requires someone to be very, very smart to find the shortest program.
Well, the thing is that this is the computer it doesn't have any return key on it. It's just a 0 or 1. So what happens is the monkey can type, and the programs must be self-delimiting. That is, the program itself decides without a further end marker when it ends. So what that means is that every Bernoulli sequence that begins with that will cause this computation to occur. In order to get that one to occur, it occurs like 4 or 5 digits more, and therefore it's 32 times less likely.
But your definition of Occam's razor now depends on your choice of programming.
Yes, however, since universal computers can simulate one another, the minimal program size is machine independent up to an additive constant. It may be a large additive constant, but I mean, nowadays people program computers and they say you have megabytes of programs.
Yeah, but they're trying to get the program as short as possible.
In
then
the
you
old
probably
days,
care about the
when you were in nursery school, people used languages like Forth, where you tried to keep, fit everything into half a byte. And a well-written program would consist of about 1,024 or less bytes. Anyway.
Of course, if the universe really is ultimately simple, then the number of bytes might be small, and it will be.
It might be really small.
It might depend on that program.
Okay, so anyway, it's machine independent, and like other entropies, it's nice for an entropy, which is the log in the program side, to be sort of have an arbitrary additive constant, and so this does too. Okay, so that's an old argument that's been had by many people about algorithmic information, about Kolmogorov complexity. Is it real or is it important? First of all, it's uncomputable, so that's another problem if you want to look for problems. But it is machine independent, but only up to an additive constant. But if you want to think about such deep and profound things, you pretty much have to make these sacrifices. Okay, so we go on. So this is the logical depth of that. Now, because a trivial orderly sequence is easy to make quickly from a small program, it's shallow. It's not logically deep. A random sequence is shallow also because it's essentially its own most concise description. Semi-orderly sequences like alternating zeros and random bits, you just merge those two ways. And this, as I say, it's distinct from Kolmogorov complexity, which is the size of the minimal program. This is the runtime of the minimal program. And of course, it needs to be smoothed out and regularized. So suppose you have two programs that are one bit longer than the minimal. There are ways of smoothing this that I'll tell you after class. But the essential idea is here. Okay, so let's go down to this thing again and say what's happening here in terms of logical depth. Now, I haven't tried to simulate the Turing machine programs to compute all this, but it is
logical depth the same thing that I call computational complexity?
Computational complexity means 12 different things according to
Well,
most people.
how many steps you have to do to get out of the
It's not.
Yeah, ordinarily, it's defined as a function class like exponential polynomial, and that's number of steps as a function of the size of the input. And here we're trying to make a way of imputing a dynamic computational complexity to a static object, in the same way that Kolmogorov complexity attributes a definitional complexity. So I'm contrasting these two notions of descriptive complexity of Kolmogorov and dynamic complexity, which is usually used in order to make it machine independent, is usually expressed in terms of functional dependence.
So maybe we should say logical depth is not the same thing as circuit complexity.
No, it's not the same thing.
There's some relation.
Yeah, and yeah, circuit complexity is a little bit like polynomial time or exponential time. These are things which are measures of dynamic complexity that are typically applied to families of inputs. That's the thing.
So if you want to produce 100 ones, what's the logical depth?
It's about
Is it
100
one
because
or
you've got a very simple program and then it just prints 100 ones and stops. So essentially, the computer has to count up to 100 and print.
Okay, so it's not just the program that says print 100 ones. It's more
No, that's the Kolmogorov
It's the running
complexity.
time of
The logical depth is how long it takes to run it.
Yeah.
Yeah. So we go back to this. Yeah, this is the object. We compute its inverse images under the monkey graph, or the monkey tree, and then we pick the shortest one, or sort of a bunch of short ones if there are a lot of them, and we say the runtime of those is the logical depth. So initially, and for some time afterwards, it's plausible to say that the logical depth of this thing increases because in order to get this configuration, there's probably no better way than by simulating this evolution, because if you used a print program, you can take extra bits to describe it. This one would say, take this periodic array, generate it, put in a little defect, and then let it run according to this rule. And that takes a little time, and the amount of time that simulation requires grows linearly with how long you let it evolve. So this is the way of applying ideas from computer science to quantify the notion of amount of dynamics a physical system has done. The dynamics of kind that can't be shortcut, because this kind of dynamics of this part here is just like an harmonic oscillator. It does the same thing over and over again. But it's just part of this larger dynamics, which is not periodic. So if you let the dynamics run for a really long time, exponential of the number of degrees of freedom, this thing will enter a Poincare recurrence. Now, as I said, it's got a conserved energy, so there's not just one orbit. There are many orbits. It has translational symmetries and things like that. So there are a lot of orbits, but not exponentially many orbits. And so the typical behavior is that it will grow into some very random looking thing like this, which is if you bother to follow it, you can mathematically one of the people here, you can see it's obeying that rule.
That's not an exponential time, though, basically.
Yeah, exponential.
It stays that way for an exponential time.
It stays that way for exponential.
Yeah, but it doesn't take an exponential time to reach that kind of.
Yes, it does.
Sure does.
Yes, it does, because even though quickly it begins to look like this, it has that simple description for a very long time until the number of steps that you have to run it gets to be n of order
But just by looking at it.
Actually doing it.
Just by looking at it.
No, you couldn't tell.
You think you got
In
this.
fact, I didn't let this one run for exponential time. I'm cheating. So the true history is no longer plausible because you would have to say how long to run it, and that's a number that is a real mouthful. And therefore, the true history loses its plausibility in terms of Occam's razor as the most persuasive explanation of how this thing got here. And that's really the idea I'm going to talk about in various combinations for the rest of the talk.
So the history has less complexity
The history,
than a snapshot.
well, the whole history just has the, you just
You can
specify
generate the
the
whole
absorbent orbit, which you might as well specify by taking the simplest case and say, generate this orbit. But a typical snapshot is more complicated. It's just like to say that a snapshot of a gas, of the air molecules in this room, has a higher description of complexity than a statement that they are uniformly and randomly distributed. Okay, so here's the digression, and in connection with the ideas that I've been hearing here about how to use circuit complexity to generate, to count the complexity of a quantum state relative to some initial condition. And I think the suggestion I want to make here is to try to bring in the same kind of separation between descriptive and dynamical complexity measures that I've done, and to use them for different purposes in the same way that I've been doing with logical depth. Now, circuit complexity, I started working on this in terms of Turing machines, where a Turing machine is this fixed computing apparatus that take inputs of any size. And circuits are used, and very conveniently, but the trouble is that a circuit sort of mixes those two resources, because in addition to saying the size of the circuit, you have to say which gates you put where, the layout of the circuit. And so that's an element of descriptive complexity, and counting the gates is, so in order to fix that problem, and then Scott is the expert on this.
Well, I'm just wondering why it's a problem.
It's a problem because when you, in some of the constructions that we do here, part of the descriptive complexity is which gates you use. For example, the fact that they can come from a continuous set. And we know that we can approximate these things with a finite alphabet of gates. But you still have the layout, and it gets more and more complicated as you get a deeper circuit. So especially when you're talking about shallow circuits, not very deep circuits, you that you do things in traditional, classical gate circuit complexity of regularizing it by saying that the layout of the gates has to be the output of a short, easily computed function. So you're not stuffing stuff into that, which.
Well, I mean, one way to think about it is, do we want our complexity measure to hit a maximum of 2 to the n, or do we want it to be able to increase vastly beyond that? You know, if the former, we should use circuit complexity. If the latter, we should use these Turing machine-based things.
Well, I'm saying you can take a circuit and say, I'm going to have an input that's of size n. I let the circuit be as long as I want, but I don't let the placement of the gates.
Yeah, no, I understand
be.
that. I understand
Okay.
that. Right.
So the way you could do that
beyond 2 to the n.
in this business is to say, we're going to give a Boolean input string. We're not going to just insist that it be a product, that it should be a particular product where we know actually how much information we're feeding it. It's one of a basis set in the computational basis. And the layout is not something we can play with either. And then we ask how many gates it takes to do that mapping. So I think that's just a clean approach. Or another way of looking at it is to say you only have one kind of gate, which is a kind of a brick, but it's like a FGPA, so you can make it do anything. So essentially the input that goes into it has to tell you what you want to do with it, and then you count how many of these bricks you need to make your circuit. Okay, so that's my digression. We're going back to logical depth and complicated and simple states. I'm going to talk about the relation of this to thermodynamic equilibrium. Well, I just spoke about thermodynamic equilibrium. I said when this thing evolves for a long time, it gets, where'd it go? Yeah, it gets very random looking. It's random in two senses. It looks random, and also in this deeper sense, it's not rapidly computable from any concise description. So I would call those two times the thermalization time and the equilibration time. They look on the surface similar, but they're really different.
Thermalization was the first one.
The quick one. It's when the gas expands and fills the whole room, but if you ran the trajectories backwards, it would all go into one side of the room before you got tired of waiting. Okay, so in thermal equilibrium, correlations are generally local and they're mediated through the intervening medium. So in other words, if I find a hot part of a block of iron, probably the stuff next to it is hot too, or will be soon. On the other hand, our world is full of stuff that isn't that way. And here I have some example. I have a couple of coins from the former British Empire. This one's from Grenada, where my daughter-in-law is from, and this one's from Canada. And they both have a picture of the same person. But the reason that they do was not that that they were ever in contact, but it has nothing to do with anything that happened to either of these coins recently. It has to do rather with a whole different person. And so they have long-range correlations involving a lot of mutual information, but without any propagation through the intervening medium. And they have logical depth, of course, and it depends on a V-shaped path in space-time. So this is just so familiar, it hardly needs to be stated. But the question of the relation of this phenomenon to thermodynamic disequilibrium. Now, I just said, I was speaking about equilibrium with this other automaton, but now let's just think about a more cosmological and quantum situation. So let's take the Earth and put it inside a reflective mirror and let it just marinate in its own radiation for a while. And then what would happen was that you certainly wouldn't be able to see anything anymore because it would be black body radiation. And the entire state of the box would be this kind of state, which is phenomenologically not classical. It's maximally, even if it was a pure state, it wouldn't look very classical. So this is in equilibrium we have something called the Gibbs phase law, which says that if you specify the independent macroscopic parameters of the system, there is typically only one thermodynamically stable phase, except when you're in the subset of lower measure, which where two phases coexist, two or more. This is evident in the Ising model, where you have the general plane in the temperature magnetic field degrees of freedom is all one phase. And then you have a coexistence that's on a line, and if you even put an arbitrarily small magnetic field, it is only metastable, and you just go to one phase. Well, now, the reason this kind of now this may not hold true for quantum systems. There are various hopeful things about how you can get at least memories that last exponentially long, with even at thermal equilibrium, which I'd like to explore. I won't solve any of these problems here. But going back to the classical case, we have this reason for the Gibbs phase law. That is to say, we have several thermodynamic phases, and the free energy depends on various parameters. As you vary a parameter, you will typically find these free energy curves cross, and as you pass through here, there's only one stable phase, because these, Murphy's law, these things, the available fields or parameters break all the symmetries, and so therefore you'll get one stable phase. However, and there are various topological ways around this, which are very interesting to study, but the way around it that is usually used in nature is dissipation. That is, a system is no longer equilibrium. And even if it's in very simple dynamics, which is not microscopically reversible, we can get dissipative systems that have a stable memory against all small perturbations. And the example of this was discovered by Andre Kuhn, and I will just maybe describe it after class. But the reason it works, well, why should it work? Because anytime you have a local probabilistic evolution, you can think of it in terms of the transfer matrix. That is, the conditional probability given this state now that you get this state at the next time. And you can take the logarithm of that and call it an interaction energy between these two time slices. So Jeff Grinsky and I wondered if this can be represented by a local potential, why is it not also obey the Gibbs phase law, and all these dissipative systems shouldn't be able to do anything interesting? Well, the answer is that if you sum, for any state of the present, if you sum all of the probabilities of the future, it has to add up to 1. So the normalization constraint on the transfer matrix means that however you vary the local parameters, the free energy stays constant. The free energy can't be changed. And so what you get is something like this. You get well, now I'm showing this free energy rising up. The reason this is rising up is because
the axis?
This is varying some parameter, like the magnetic field. The bias in one of these dissipative rules. And what you have here is both phases are stable. But then if you push too far, you get the nucleation and growth of the metastable phase. But that occurs not because of this reason, but because it's metastable. And, well, this could be described in a D+1 dimensional system too. But in a D+1 dimensional system, the metastability can exist over a finite interval, and the free energy curves are non-analytic. Well, so that's the way it normally happens. One thing I'm really interested in is connecting the extra ways that quantum mechanics can stabilize memory, and perhaps even stabilize computational evolutions, to the question of whether, to the ways that can be done classically, which is chiefly by dissipation. I think there's no other way because of these arguments. The local classical system of thermal equilibrium is just not going to stay interesting. It's going to be at best metastable. So where does classicality come from? This is the sort of the idea that is, Wojciech, where is he anyway? It says, right there, yes. is pioneered under the name of quantum Darwinism, and I like to call it quantum spam.
Those are Wigner's friends?
No, not Wigner's friends yet, yes. One of them would be Wigner's friend, yeah. Okay, so, but anyway, the idea is that it's intrinsic in quantum mechanics, that if you have the environment eavesdropping on a system in a commuting way, and the environment's out of equilibrium, you end up with replication of information in one basis and obfuscation of it in others. And Riedel has pointed out the role of non-thermal illumination in bringing this about. And as I said, though, if you trapped all the photons and let them be reabsorbed, the system would lose this quantum Darwinist nature, its cat-like nature, and it would lose its classicality, and it would, in the course of doing that, it would lose its complexity. So I said that if you run a system for a very long time, and I was lying about the exponential, I mean, if you ran it for, I could generate a good characteristic. The way to do this is to toss some coins to generate the initial condition. Then it would be kosher. But anyway, conversely, a deep structure that seems to have had a long evolution might have come from a short evolution instead. And this is the Boltzmann ring problem. How many here have not heard of Boltzmann rings? Oh, you all have heard. How many have heard? Okay.
I mean, my current state is consistent with my having heard it.
Yeah, okay. All right. You took away my next question is how many people here are Boltzmann rings? Okay, you're right. Okay, so anyway, people care, cosmologists care about Boltzmann rings. And the diabolical dilemma that they pose is that although they explain the arrow of time in a way, they don't explain why we should believe anything that we learn from science. Because this is shown Carol's diagram that he had from a New York Times article, that if we say the reason that we're here is that there was a fluctuation in a very large universe, we think we do live in a very large universe now, and this was our past and this is today, this past is less plausible than that past, which says that it's not 14 billion years old, it was much less, and it just happened locally, because we don't have anything we have nothing here except what's local. The only thing our telescopes see are the photons that come into it, or the gravity waves that come into it. You can have fluctuation in gravity waves too. So the people actually worried about that in the 19th century, equilibration, because it would be the heat death of the universe. That was a gloomy idea as opposed to continue in progress forever. But it's already a problem in the present, because if you are living in a world that ultimately is going to equilibrate, if you either in a closed energy, microcanonical or canonical way, you have to make the additional postulate that you are atypically early in history, and if you're going to believe anything. So let's think about that kind of postulate. Well, this is actually something probably more worth worrying about than whether we're Boltzmann rings, and that is that if we look at the time that the Earth has been around, we're roughly in the middle or maybe a little toward the end of the time before the sun gets too hot. And life came on the scene pretty early in that time. Complicated life came rather late, and civilization is very recent. So we might say, why are we so early? So the various answers are things like civilization is unstable and tends to destroy itself. And of course, we can think of rather small modifications. I mean, I can think of small modifications in other people. I would not require any modification myself in order for people to be more cooperative. Or we could colonize space. And of course, those are small changes, but perhaps we're not in the place where those happen quite right. There could be other places in the universe where it's a little better, enough better that civilization is stable. But ours is stable enough to have produced us, but maybe not much more stable. And this is supported by this idea that if this stuff is very rare, less than 1% whole body, we wouldn't see the remains of old civilizations that failed or the communications. But if you talk to David Deutsch, he says, no, I mean, I didn't quite put this question to him, but he emphasizes the idea that new things keep happening. So perhaps a billion years from now, there will still be people, but they'll be worried about, like, there's been a year and a half since the latest Apple product, and that the world that they know is, and that these products have been around for a good while. I will not disparage the products of competing computers. Just strike that from the record. Anyway, there's something about the world, like they just discovered how to tweet or something, and how. I don't believe this. I'm really more in sympathy with that. And let's go back to that. And I think that this was drawn to my attention by Alejandro Jenkins. That is that the anthropic principle, which 20th century physicists think they discovered, cosmologists, was probably discovered in the 19th century, put into a form by Schopenhauer. And he has a lovely quote, which I can't fit on all this page, but he says that he was writing this in rebuttal of Leibniz, who was trying to say that God created the world in the best possible world so that for the benefit of his beloved humans. And Schopenhauer, whose life was rather pessimistic as well as his philosophy, said, go on, this is crazy. We live in the worst of all possible worlds, meaning that if you changed anything a little bit, it would probably destroy itself. And so he gave a number of examples. He said if the planets had perturbations in their orbits that didn't die out. He said if the composition of the atmosphere changed slightly, etc. You got to go through a whole list of things. And then he says, and this is a few decades before Darwin, the fossils of these other species are evidence of worlds that are a little worse than possible, and that's why they're not here anymore. So if you think of this is, let's take an optimal world of the kind that Leibniz proposed and expand the goodness of this world into lowest order around the maximum. And then you put a plane here of zero goodness, meaning if it's any worse than that, it'll destroy itself and there will be no observers around. So it is kind of ironic that actually Leibniz figured out how to figure out the area under his cap. And Schopenhauer, who wasn't even a mathematician, figured out that he didn't come up with this formula, but that if you have D parameters, it's only about 2 over D, the expected goodness of the world. So anyway, here's the impossible, it's down below it, and we won't even see it. It doesn't happen for us. Okay, so
assuming everything's nice and smooth.
What?
If we're right near a phase transition, and that's why we're on the verge of destruction, it doesn't say anything about the goodness of the present existence.
Well,
We're just on a cliff.
if the probability of occurrence of the phase transition is well, are you talking about a vacuum phase transition?
Not a vacuum phase transition, just something where goodness has a sharp click instead of being smooth.
Yeah, you can use when I say post-18th century mathematical tools like Lifshitz continuity if you want to argue about things like that. Anyway. Yeah, what is? Okay, well, this is a good thing. Well, it's not quite a good thing study, is it? Okay, so anyway, what do you say? Well, I think I won't talk about big restraint because we don't have a lot of time. So the worst of all possible worlds is this natural manifestation of high dimensional geometry. Now, maybe this is sort of what you're thinking. An even more pessimistic notion is that we may be beyond the boundary, and we're just lucky, and it hasn't happened yet. And like, if our ability to have a complex civilization depended on something like a pencil balancing on its point in a really
So infinite fine tuning, I would say, undermines science in the sort of the same way as both grades. Now, how can we get away from this? Now, there are various ways of getting away from this. You can try to come up with models that in which you average in some way that doesn't permit equilibrium to occur. I don't know about that because I've just become a follower of cosmology in the last couple of years. But what about if it really doesn't work at all, why don't we fall back on defining the set of all possible universes in a purely mathematical but not tainted by physics? And in fact, we can use the monkey tree for doing that, and Schmidt-Huber suggested that you have an algorithmically based theories of everything based on that kind of idea. But in a way, that's too easy an answer because I already showed that tree is, by its universal self-similar structure, we know that a positive fraction of the loads in that tree are complex or deep, but by any criterion, however we define a criterion, we can show that it fills up a positive fraction of that tree. So that's sort of making the problem go away too easily. But maybe, so we want to put some physics in, but how much physics? And this is the sort of the hardware-software distinction, or the initial condition laws of motion distinction. And one of the things that might likely be put in addition to all the things that I like reversibility, superposition, and we're making a lot of progress on locality, how to get that out of the tank. What about fault tolerance? And that's a little bit quite connected to the lack of infinite fine tuning. And so Conway's game of life is universal, but it's irreversible and it doesn't look very fault tolerant. Peter Gotch, who's going to give a remote talk later in this conference, worked on probabilistic one-dimensional cellular automata that are very strongly self-organizing. They're dissipated. So you have to, if you want to put them in the universe somewhere, you either have to exploit some funny things in quantum mechanics that give you complicated non-equilibrium states, states that are at equilibrium but still complicated, or you have to find a place in the universe that stays dissipated forever. But so that's a thing to look for. So he's shown that in his talk will say that they're even in one dimension, locally interacting, computationally universal, noise tolerant, meaning that all the local transition program will be positive, and stable. They not only can do that if you set them up in the right initial conditions, but they can self-organize into an arbitrarily complicated state. So that's a thing worth listening to. And when you hear it, think about how you would embed that kind of self-correcting architecture into the manifolds that we think about in cosmology, that are quantum and are certainly not Euclidean. Okay, so that's the, now I have probably 0 minutes, right? Okay, that's a good place to stop. If you want to ask me about Victor's friend, ask me, but I might not remember the answer.
Urgent question?
I was just asking, you had this point about infinite fine tuning. I mean, suppose there's a way to find it with short input, and you just have an algorithm for finding that. Wouldn't it have low algorithmic complexity?
Oh, you mean?
I mean, you said infinite fine tuning undermines science as much as the same way as Boltzmann brain. But I was just curious how, because naively I would think if you get an algorithm for finding, for solving for what the infinite fine tuning is, then couldn't it have low algorithmic complexity and therefore high probability by your criteria? Right?
Only if you have something that will impose that fine tuning. Like if you had a universe within which you would say, we'd like the cosmological constant to be close to 0. It isn't now, let's fix that. So even knowing that it could be,
Right.
yeah, in fact,
But couldn't that just be part of the, I mean, if we're
in
saying
fact,
the
you
laws
say
are
that
simple.
already.
But if you're just saying that the probability is high if the laws are simple, couldn't this at least be one way that it's simple?
That's similar to the idea that we can
what you were saying was that we make the fine tuning, if we know what the fine tuning is, we could make it. Or it would occur with high probability in the monkey tree. That was the reason I didn't like the monkey tree, because for trivial reasons, if we can say a place that we like, that place has positive probability. But whereas, and that's why the question is too easy. We're in a universe and we say, we think it's accidental and arbitrary or distributed from a large set. We may be privileged observers sitting here, but are we privileged in some nicer way than having just been extraordinarily lucky so far, and the whole thing is going to crash in a millisecond?
All right.
Okay, maybe we can take the discussion to the break.